All right, good morning, everyone. We have more than 30 people online as well, so hopefully the room numbers increase as well. Let's get started. Today's seminar, we have Peter Hennings. Peter is a research professor and lecturer here at UT. Between 2016 and 2024, Peter was PI of the CESAR consortium here at the Jackson School, and he also teaches at the Department of Earth and Planetary Sciences. He continues his affiliation with CESAR as an advisor and researcher. He just recently switched with Katie as a PI position. Prior to joining UT, he spent 25 years in the petroleum industry, where he worked as a research scientist with Mobil and Phillips Petroleum and research manager at ConocoPhillips. He received a BS and MS degree from Texas A&M.
Sorry about that.
With a strong recovery then from UT Austin with a PhD. His research interests include induced seismicity, structure geology, seismic structure analysis, reservoir geomechanics, and geology of West Texas and the Rocky Mountains. He has taught over 100 classroom and field courses and professional university undergrad and graduate level on seismic structure analysis, fractured reservoirs, geomechanics, petroleum systems, induced seismicity, and field methods. And Peter today is going to talk about injection and induced seismicity in Texas. Peter, take it away.
All right. Andras, thank you very much for allowing the talk and the postponed talk from last week as well. And it's my goal today, it's really an overly ambitious goal, to try to describe how the Bureau came to where it got to in 2015 and 16 with induced seismicity in Texas, and then what has happened over the last 9 years or so with the formation of CESAR and the research that CESAR has done. So I won't get through all the slides, and I know that. I'll stop when we need to, and there's still time left for discussion, and that's just sort of the way it's going to go. I do very much appreciate the changing of the guard that has happened just in the last few weeks. As Andras mentioned, you saw last Friday, Katie Smye is now the PI of CESAR, and I've stepped into an advisory role. So what I aim to do over the next year or so is to be an individual contributor and advisor and help with that transition. And I really like the idea of being an individual contributor. It's been about 30 years since I've had a chance to really just fulfill that role, and so I appreciate the change and the organization's support for that. So I have, 25 co-authors, I suppose, on this overly ambitious talk. But it really comes down to this adage, that when you produce fluid from the subsurface that we've all learned so much about, you learn some things, but when you inject fluid, you learn far more because you actively perturb the system. So Moen last year published this diagram, which is a nice cartoon. It shows the context of anthropogenic induced seismicity. It has depletion from conventional fields on the left, hydraulic fracturing of unconventional resources, geothermal, mining, wastewater disposal, and underground gas storage. I'll be talking about wastewater disposal almost exclusively, and reservoir impoundment. Thinking of what the Bureau researches now across our energy and environment space, all of these topics, maybe except for reservoir impoundment, are very germane to understanding the response of the subsurface, and especially induced seismicity that can be so problematic in the eyes of the public and in the eyes of the industry from an economic standpoint. So getting here, and my time working on this topic has been this really amazing experiment that has been conducted by the petroleum industry over the last 20 years in the mid-continent. It's the injection-induced fault rupture and seismicity experiment. And over this time, there has been all of this injection and all of this recent seismicity. So on this map of the lower 48 in Canada, there are two map layers. The black earthquakes of magnitude 3 and higher are on the uppermost graphics layer And the red earthquakes of magnitude 3 and higher are on the background graphics layer. So this shows the earthquake history since the advent of seismologic instrumental recording in the 1970s at a magnitude 3, because at magnitude 3, there was a sufficient network capable of detecting earthquakes across North America such that really no magnitude 3 or larger earthquakes would be missed. So this represents relatively a complete history of earthquakes at that magnitude floor. So then you can see in the graph underneath the map the rate of earthquakes of magnitude 3 that happened from the 70s through to 2009, and then the rate of seismicity that began in 2009 through last year in red. And clearly, a lot of anomalous seismicity occurred, and principally where you see the red poking through from behind the black in the mid-continent of the United States here. There have been something on the order of 4,000 of these magnitude 3+ earthquakes in the last 20 years, and 6 magnitude 5 earthquakes and larger in just Oklahoma and Texas in the last few years. So what has happened is these areas of anomalous seismicity have been studied, probably 200 scientific publications, maybe 250 over the last 15 years or so, that divide the seismicity into these systems, all the way from Ohio down through the mid-continent in Texas and up into the Rocky Mountains. And we'll talk about these systems and this history in Texas in the talk. But by about 2012 or 2013, it was very well understood that massive injection into deep reservoirs of oil field wastewater was the primary driver of this anomalous seismicity. And Ellsworth's 2013 paper really set the new era of induced seismicity in terms of publications. Now, I'm not going to talk about Oklahoma, really. The rates of seismicity there were the greatest of any of these impacted areas, and their earthquake rates were higher than California for several years at magnitude 3 and higher. But even Texas joined that club in 2022, had more earthquakes of magnitude 3 and higher than natural seismicity at our active tectonic boundary in California. A few years ago, Rex Buchanan, Michael Young, and Kyle Murray worked with many of us to publish a GSA special memoir of papers outlining the history of what happened in the induced seismicity space, what the industry and the regulator and research response was in Arkansas, Oklahoma, Texas, New Mexico. And just want to point out that this volume exists, and I'll come back to it a bit again later. So Mark Zoback and I are working right now on a kind of a look back at this experience of the great injection geomechanical experiment, and we're comparing Oklahoma, Fort Worth Basin, Midland, and the Delaware Basin. The injection history of those 4 areas is shown at the same scale for these 4 plots in blue. The cumulative injection is shown as this purple line, and then the earthquake rates per month are shown in black. And so, without going through a lot of numbers in comparing those areas that have experienced this injection and seismicity over the last 25 years, you can see the relative scales of where there's been the most injection, the highest earthquake rates, and the wide variation in response of one system against another. But clearly, all of these areas started to experience this anomalous and problematic seismicity when the rates of injection got above 2 and up to 4 million cubic meters per month. That's when, in all of these systems, some of the problems began. So we can come back to that later if there are questions on this. Anyway, in the course of that time, 22 billion barrels of oil field wastewater has been injected into lower Paleozoic carbonates in 4 basins. That's 1 trillion gallons of oil field wastewater that has been injected. So, what's important geologically? kind of what we're all about here, of course, is stress in Earth's crust, and stress plus faults makes earthquakes. So intraplate stresses vary generally smoothly across cratonic domains in the United States and in Canada, going from compressional stress states today through strike-slip in the mid-continent and to normal faulting regimes in the Permian Basin and the Gulf Coast. And then that transitions again, of course, to strike-slip as you move towards the western coast. Zooming in, and this is using a lot of Lunsney and Zok's work. Here's a blow-up of the stress state of Oklahoma, where strike-slip faulting predominates, down through Texas, where a lot of these systems have a transitional strike-slip and normal faulting regime, down to the Gulf Coast, and normal faulting, of course, along the Texas Gulf Coast tectonic margin, and then normal faulting as well out in West Texas, where on the western edge of the Delaware Basin, it's being impacted by the active Rio Grande Rift today. So there's the smoothly varying transition in stress style, and there's also a smooth transition in the orientation of the stresses, and these red lines represent the orientation of the maximum horizontal principal stress. And you can see those bars smoothly curving as they move from Oklahoma to Fort Worth to the Gulf Coast and out to West Texas. And you can also see in the Delaware Basin, there's a lot of heterogeneity. And as you move from the south to the north, there's nearly 180-degree, rather smooth rotation of SH max just along that distance across that basin. It's enigmatic and very important. What's also important are faults. Earth's crust is ubiquitously faulted. The sedimentary realm of our basins, like this view from Moab above, and then, of course, the basement. This is Lily Horne's ongoing interpretation of some seismic data in West Texas showing faults in the Proterozoic basement and an important earthquake sequence here. Earth's crust is ubiquitously faulted. And it just so happens across the mid-continent, those pre-existing faults find themselves today in a stress state that is critically stressed, which is why we end up with the seismicity. So this diagram, this cartoon, is supposed to kind of encapsulate the problem that we deal with in this space. So if you just bear with me, I'm going to kind of run through this in some detail. Here's a green well that is drilled and completed horizontally in some shale layer at depth, and it's hydraulically fractured as an unconventional well, and it's quite commonplace for those hydraulic fractures to directly interact with existing faults to cause pressurization and rupture and seismicity. And that seismicity may actually travel up and down the fault, especially down the fault, quite a great and surprising distance. Of course, then we have flowback of the frac waters and maybe also co-produced water that has to be disposed of. That fluid comes over here in the diagram, and that disposal may occur in shallow levels where we may have stratabound faults and pressurization, or it may go down into deep saline aquifers that sit directly on top of the seismogenic basement, and pressurization at this level can destabilize these basement-rooted faults that typically do connect with the deep aquifers, causing instability and rupture there. This is by far the scenario that has created the most problematic earthquakes in the mid-continent. Deep injection into saline aquifers above the seismogenic basement, causing and destabilizing existing faults in basement to rupture. And those ruptures may propagate several kilometers down those faults into basement. Another context is shown here as well. This is conventional oil production where petroleum is produced from a level and then the co-produced water is injected back down as secondary recovery to maintain fluid pressures, because those oil fields are typically operated with a volume balance of 1 to maintain pressures. Those types of operations are not generally associated with induced seismicity that's problematic. So then what we care about is faults and reactivation of faults. Here's an idealized fault with an offset horizon, and along the fault there are some yellow analysis points, and at those analysis points we care about the resolved stresses, the shear stress and the normal stress and the pore pressure, and then slip occurs when the shear stress normal stress ratio, This little equation here exceeds the frictional resistance to sliding, more Coulomb construct. And you can rewrite that into the Coulomb failure function. That's this equation here. So what we care about is the shear stress, the normal stress, and the coefficient of friction at these points of analysis. Of course, the normal stress is impacted by the pore fluid pressure. That's really the sum of the problem in its simplest terms. So what's happened in Texas? So back to this magnitude 3 and higher earthquake threshold to investigate the history. Here is Texas with Lily Horn and her colleagues' new map of the top of basement shown as contoured, the impacted areas looped by basin, and then some of these important earthquakes shown. A couple that may have been natural, certainly the 1931 Valentine 5.8, way out here in far west Texas. But then these other earthquakes since then as being researched and concluded as induced. So then on the lower graph, the black line in back represents again that monthly rate of 3.0 and higher earthquakes in Texas. And then the dashed line represents a 6-month moving average of that black line. So that's the earthquake rate. And contributing to that earthquake rate back in 2010 and 2012, brown means the Midland Basin is contributing. Then there was this period of time from 2012 until 2016 when blue, or the Fort Worth Basin, was the strongest contributor to that earthquake history. Those were the problematic earthquakes in the Fort Worth Basin that got the whole thing started. TexNet and scissor and all the political pressure to do the monitoring and the research, because those earthquakes in blue were happening under the populated Dallas-Fort Worth area with 9 million people, many of them feeling these earthquakes. And then since then, though, in more recent years, the earthquake rate as it was driven to its maximum in 2021 was driven by seismicity in the Delaware Basin, this amber curve right here, but with important contributions from the Eagleford shale play and induced seismicity from hydraulic fracturing, and also in brown, the Midland Basin continuing to play an important role. So here's a blow up in the upper right of just the last 5 years. A lot of earthquakes, a lot of problematic earthquakes you can see in magnitudes up here, above magnitude 5, including a couple just last year in the Midland Basin that are especially notable. But what this chart really shows is an amazing success story. Using the monitoring data and the research, proactive engagement from the industry, and actions by the regulator, the Railroad Commission in Texas, and the New Mexico Oil Conservation Division, that earthquake rate now at magnitude 3 and above in Texas is lower than it's been in the last 5 years. And that is because of the changes in practices of injecting this wastewater in those deep saline aquifers and redirecting that injection into other targets for disposal. That doesn't mean that, the case is closed and all the rest of that. Monitoring has to continue. Some of these large earthquakes are certain to continue. But what it demonstrates is there is a broad understanding, there's the will to take action, and there is the result in mitigating what was a very problematic rate of earthquakes, now down to a level that is becoming managed. So, in this talk, I've tried to throw a lot of the publications in that matter. There's no way to put them all in. I think it's interesting that here at the Bureau, the work on induced seismicity goes all the way back to the 1980s with thesis work by Davis, publications by Davis and Pennington and Carlson, working on the eastern shelf of the Midland Basin, Cogdale Field. Even the venerable structural geologist Todd Harding was working on Cogdale Field back in the 1980s. This is all really nicely described in Cliff Froelich and his colleagues' historical review of induced earthquakes in Texas. That was published right about the time that TexNet and scissor were coming to be. But there was important work going on here at the Bureau. Peter Eichelbohl and postdocs and Julia Gale were working on earthquakes in East Texas at this time, before the modern era really got going. And so there's really quite a rich history of addressing this topic before the TexNet scissor era started. So this is the first presentation I made when I came to the Bureau in February of 2016. I just found these slides the other day as I was trying to figure out what to talk about today. And so this is like some history. But what it shows is that in May of 2014, Representative Myra Crownover in the Energy Resources Committee of the House of Representatives in Texas held a committee, and the committee was on the House Resources Committee on Seismic Activity will hold a hearing. They were holding a hearing to understand what was going on in the Fort Worth Basin and other impacted areas in Texas. So in 2014, the political pressure was starting to build. That's about the time when Scott Tinker and Michael Young and Jay Kipper and others here at the Bureau started to work with other units at UT, the Institute, Petroleum Engineering, to propose what the University of Texas might do. And by February of 2015, 9 months later, the Dallas Morning News reports, after interviewing Scott and others, that the university is standing by to start to address the problem with monitoring and research. And that came to fruition after a lot of hard work by all of those names by June of 2015, with the legislative appropriation of about $4.5 million to form TexNet. And so I'm just going to read this down here because I think it's kind of cool. That $4.5 million appropriated blah, blah, blah for a 2-year period beginning on this date for the deployment of seismic equipment, the maintenance of a seismic network, and modeling of reservoir behavior for systems of wells in vicinity of faults. Pretty specific language. What it does is it creates the latitude for research, not just monitoring. It creates the latitude for research, which was then, of course, what happened. So TexNet ended up with its very modest early goals. Alexandros was hired. Scott and Michael and Jay and others had the idea that there should be an industrial collaboration formed at the same time to mirror the legislative side. And so the Center for Integrated Seismicity Research was proposed to industry. And then some hiring was done. And so here's what the TexNet and Scissor, quote, science team consisted of back in early 2016. There's Alexandros Savedas and a technician to be named. TexNet now has like 20 people in it or something. And then here's what would become Scissor: Peter Eichelbohl, his postdoc Xikeng Fan, Julia Gale, already working on the problem, and I joined to get the whole Scissor thing going, and then all of these other collaborators at that time. It's kind of a ready-made organization, but it would change a lot over the years. And that change, the TexNet-Scissor collaboration, is discussed at some length in a paper that Michael and I wrote for this special volume in GSA. It kind of covers a lot of this history. This history, though, to me, it's in contrast. So when I think about the Bureau, and even when I thought about the Bureau at that time, it was puppies and rainbows. I mean, the research done at the Bureau, for the most part, was about opportunity, about resource. Where are the hydrocarbons? How do these rocks host resources? What are we going to do to sequester the carbon? All of these kind of opportunity-based research topics, even the economics of that. But Scissor and TexNet was not puppies and rainbows. Scissor and TexNet was a world of barbed wire and rattlesnakes. And it really was, for the first 3 years, it was a very contentious thing. As the research was started and reframed, the monitoring began, industry weighed in, and the whole thing started to get some momentum. But TexNet and Scissor worked collaboratively as sort of one organization for those first probably 4 or 5 years, and then we've since separated into distinctly separate organizations, the TexNet program and the Center for now Injection and Seismicity Research. But But that's that history. So TextNet is not my story to tell. That's Alexandros and his colleagues' story to tell. You know, they've got 250 seismometers out now. The original legislative funding was for 22. It's kind of an amazing journey that they've taken, and they maintain a large package of cutting-edge seismologic research as well. SISR. So the goal of SISR in the yellow up there is to characterize the intersection of natural factors and anthropogenic drivers that cause dynamic changes to reservoirs, so that stakeholders can mitigate the hazard of induced earthquakes, threats to the surface environment, and therefore challenges to sustainable energy development. So Katie showed this slide on Friday. Here are the people that currently are in SISR or collaborate with SISR, and then the corporate sponsors on the right-hand side. We had 30 sponsors last year. That's a number that won't run into the future because of mergers and changes and asset rationalizations and all the rest. You can see some names grayed out here now due to mergers. Endeavor, Marathon, Pioneer don't exist anymore, but new companies are coming in. So let's see. The SISR website, which I won't go to now, is live, and on the website you can find like Lily's new fault maps and Amanda's geological models, and JP Nico and Junga and Tim Lang, their pore pressure models, and are all sort of nicely organized along with all of the SISR projects on that website. So in studying induced seismicity, just like everything else we do at the Bureau, it's deeply interdisciplinary. We have to have multiple types of geophysics, from instrumental and analytical computational seismology, of course, active source seismic science, acquisition and interpretation, all of these different topics in geology, hydrogeology, aerospace engineering, earthquake engineering, data science and analytics. It's kind of, to me, it's a humbling, kind of amazing space to really address this problem. So what kinds of things do we study in looking at injection-induced seismicity in the mid-continent? So this is an example from the Fort Worth Basin. It was the project area that was already under study when SISR and TextNet joined the scene. And then here's some of the work we did after we joined. So in the Dallas-Fort Worth area, between about 2008 and 2016, there were a dozen or so problematic earthquake clusters that developed. They developed due to injection of flowback water from hydraulic fracturing the Barnett Shale into the Ellenberger above basement, causing pressurization and the reactivation of existing normal faults. And you can see these real earthquakes along these normal faults propagating downward into basement. On the chart down below are SMU's hand-curated seismic monitoring data representing all of these different earthquake clusters that developed over time from 2008 up through 2019. The injection rate is shown in the solid black line, and the cumulative injection is shown in the dashed line. So that's the injection and earthquake history. So what we want to do is to try to put everything together to develop a comprehensive laboratory for understanding what the causative mechanisms are. So here are a few of the projects and the publications that we joined or we worked on. Many of these Bureau publications on the left to characterize the earthquakes, understand their spatial and temporal development as clusters, redefine the stress state in the Fort Worth Basin, remap the faults in 2D and 3D, understand the reaction of those faults in the modern stress field, recharacterize the injection reservoirs and build geological models, translate those into models where we can simulate pore pressure. And here you can see this anisotropic, structurally defined permeability model that's calibrated with thousands of wellhead, primarily wellhead pressure measurements to generate something that we can then use. So it took like 12 publications to get us to the point where we could then look mechanistically at what's happening in the Fort Worth Basin. So what we see in this map is the maximum change in pore pressure that occurred in the Ellenberger group as a function of injection from these blue diamonds. And then you can see the location of faults and these problematic earthquake clusters in purple. Taking one of these examples, the V here is in Venus, Texas, in Johnson County. And in this location, here's the change in pore pressure over time. Here's time on the bottom. And you can see the change in pore pressure going up, up, up until the very first earthquakes occurred locally at that Venus cluster. The amount of pore pressure change associated with the onset of the Venus earthquake cluster was about 40 psi. That's like the pore fluid. It's like the pressure you would ride your road bike, maybe not even road bike pressure tires. You can also see that from 3D analysis of faults, the fault area at criticality as the pore pressure increased as well until it got to over a square kilometer in size. Looking at the the Azle case over here, it's pretty much the same story. Here's the pore pressure increasing over time until the earthquakes began. And that pressure, again, is in the 40 psi range. And here is the fault area at criticality that grew as those pore pressures increased. Both of those cases are proximal. The injection and the pore pressure change and the fault reactivation, the earthquakes, are all happening in a local area, right near the injection. But there's this case in the Fort Worth Basin, as there almost is in every one of these cases in the mid-continent, where there are earthquakes triggered at a great distance that can't be explained by any kind of conventional stressing mechanism. Diffusion-based pore fluid transfer doesn't get there. Poroelastic stressing doesn't get there. The only way they can be explained is by, in my opinion, is by the movement of pressured fluids along faults. It's really the only explanation left after all of the research has been done in getting some kind of a mechanism to right under the Dallas-Fort Worth metropolitan area and causing this distal earthquake sequence below, proximal and distal. So I'd like to add, though, that this analysis was done using just all of that compilation and modeling and effective stress. More full physics modeling was conducted over the years. Madi Haddad and Peter Eichelbohl in several papers looking at some of these same earthquake clusters, Texas A&M contributing as well. And so those are more full physics computational models of very much the same sorts of processes. Okay, so there's an example of what we've attempted to do and replicate several times, moving on to, like the more important story now. So what's going on in Earth's most prolific water field? As Katie and Mark showed in the meeting last Friday, CISR has a series of publications that we filled the December AAPG bulletin with. The Geology of Injection-Induced Earthquakes in the Midland Basin region. And just going to the first two papers Katie has a paper on understanding the water challenges of production and injection. And then Katie and I have a paper on kind of what we really think we know about induced seismicity in the Permian Basin region. And this graphic, this beautiful graphic, was done by Sharon Mosier's PhD student, master student, Ben Davis, who now works at Diamondback Energy, sketching the injection domain in the Ellenberger overlying this amazing complexity in the Proterozoic basement. So, Katie's paper, she talks about and reminds us about the distribution of conventional produced water. This has been 100 years in the making. This conventionally produced water is generally injected back down into the oil-producing reservoirs, causing a net pressure change of 0. Here's the footprint of the unconventional produced water, though, in the Midland Basin and the Delaware Basin. And Katie also shows us the cuts of water and updates this from some important work that Bridget Scanlon and her colleagues had done before, showing the distribution of water cuts in the Midland Basin and the far wetter Delaware Basin, and then where that water is being injected today. Shallow injection, according to that schematic diagram, is shown in amber. The deep injection is shown in purple. And at the same scale on the right-hand side, these two graphs, you can see how the injection in the Delaware Basin really far exceeds the injection rates in the Midland Basin, while the deep injection is about the same for each. Okay, so in a summary paper that Katie and I put in that volume, we divide the Permian Basin into 7 earthquake systems, with an earthquake system being defined by us as earthquakes induced or triggered by a specific set of anthropogenic agents that interact uniquely with extant geologic elements in an understandable spatial temporal context. So we divide it into one earthquake system up here, primarily in New Mexico, another one down here in Texas on the western side of the Delaware Basin, the southern Delaware Basin, one on the Central Basin platform, the Central Midland Basin, and then a couple of these on the eastern shelf of the Midland Basin. And then here's that same type of chart that you've seen before for just this area. And this line is what I'm going to show you in a minute, which represents a data compilation. So here are the earthquakes. And of course, TextNet standard catalog is a TextNet high resolution catalog. This happens to be a catalog of proprietary data provided by scissor sponsors that uses a high resolution velocity model, an anisotropic model, and TextNet data, and a lot of additional seismic stations. And then the red areas represent the areas of regulatory action. Regulatory action in Texas, here in the Delaware Basin, and over here in the Midland Basin, and then regulatory action in New Mexico. These actions have taken place over the last 3 or 4 years, serving to curtail primarily deep injection. A paper that I really love that came from the early TextNet and scissor collaboration was led by Cliff Froelich, and was really Cliff, the seismologist up at SMU, and a lot of the rest of us. What Cliff did is really elegant. He took the data from this one station operated by SMU for national defense that has several seismic stations in one patch of ground. And he used this extremely good record of just this one set of stations down here to locate all of these earthquakes before the TextNet data became available, because this record began in the year 2000 and gives us a chance to understand the rate of seismicity in the Permian Basin for the 17 years prior to when TextNet then started to provide its high-quality data. And so it gives us a chance to ask the question, well, when did the seismicity really become anomalous in the Permian Basin region? And the answer to that is early 2010. Just as unconventional development in the Permian Basin region began. And you can see the rates of hydraulic fracturing in green and wastewater disposal in some of the other colors, and then the earthquake rates over time. And so there was a pulse in 2010, 14, 15, and then finally joining the TextNet era in 2017. Okay, so looking along this transect is this pretty complicated thing. So this represents sort of a cross-section, but what it really is a data projection with all of the data in the Permian Basin projected into one common plane. So at the shallowest level, we have sized by volume all of the shallow injection. The blue represents hydraulic fracturing completions. Purple represents deep injection. Pink represents the sediment basement interface. And then below it and even above are these earthquakes, TextNet earthquakes in black and gray, and then those proprietary earthquakes in green. And so you can see where the earthquakes are, and I would say focus on the green for now. They're pretty much beneath the basement sediment interface in the western side of the Delaware Basin, way up in the sediments in the southern side of the Delaware Basin, and then like the western side of the Delaware, the Midland Basin has earthquakes down in the basement. So we need to talk through that. One way to think about this is, well, just how far above and below the basement sediment interface are these earthquakes? Out here, in the western side of the transect, where you see New Mexico data, and then this cluster projected into the cross-section, we have these earthquakes that are down in the basement. And the research shows that it's the injection into the lower Paleozoic carbonates that has triggered that seismicity. And we'll come back to some of these other areas as we go. So Katie published a paper last year, which was really a collection of components like you saw for the Fort Worth Basin, but in one paper, needed to kind of understand how injection into these deep saline aquifers in New Mexico and down into Texas is responsible for the formation of what we call the Culbertson-Mentone earthquake sequence and other earthquake sequences up here along the state line, occurring with a few MPa of pore pressure change, according to this pore pressure map by JP and June Ge. And then also, here's a profile of Lily's ongoing seismic interpretation, which puts some context to some of these earthquake sequences, along with her interpreted Grenville age imbricate thrusting down in the Proterozoic basement. So injection into this strata right here, coming in contact with faults, changing the stress downward, causing triggering of seismicity below. Okay, so those are two systems, one proximal to injection and one distal to injection in the northwest side of the Delaware Basin. So then we get to more of these papers in this volume, the Midland Basin now. Amanda has a paper in the volume where she shows us the distribution of facies and pore volume in the deep injection strata, all the way from the Ellenberger up to units of Pennsylvanian age. Lily has a paper on the fault interpretation, basement-rooted faults in the Midland Basin, showing not only where the faults are, but where they tip out upwards into the base of the Wolfcamp Shale, which is very important to understand the vertical distribution of the faults, understanding which faults have been seismogenic, and understanding what their slip hazard is today. JP and June Ge studied from Amanda's geological model the pore pressure increase associated with this injection, which is shown on the right-hand side here. There are many areas in 2016 that had already experienced 2 MPa of pore pressure increase, or 300 psi, and then in more recent years, there are some areas that may be up to 700-800 psi pore pressure change. And then I contributed a paper kind of putting things together, the pore pressure and the faults and the seismicity from a variety of earthquake catalogs, looking at 21 earthquake clusters out here in the Midland Basin and what the history of injection and every one of those earthquake clusters consists of. So how the pore pressure ramped up gradually or ramped up suddenly, and how the earthquakes were associated with that, and then what the variation in pressurization is as those earthquake sequences evolved. So what we can see in general, though, is as the rate of deep wastewater injection increased, of course, the rates of earthquakes increased, and probably most importantly, the length of critically stressed faults increased. We're taking a system of existing faults and turning that into a more hazardous system of existing faults with that pressurization. Okay, so that gets us really across the transect as far as deep injection triggering basement-rooted seismicity. And this is a compilation by Katie that shows these geological models and the pressurization and this seismicity that is occurring as the Ellenberger and other formations become pressurized, destabilizing faults. So this is really the consensus now. I mean, there's a lot to do to understand exactly what's going on, but deep injection causing 2 of the systems in the Delaware Basin and 3 of the systems in the Midland Basin really is almost certainly what is happening. So that means that understanding the nature of what's going on in the basement is really vitally important. Where are the critically stressed faults? Where are the faults that can transmit pore fluid pressures laterally and vertically? And how can we use our scant data to map those systems. So Lily's been making her way around the Permian Basin, from the Delaware Basin to the Midland and back to the Delaware Basin now, trying to integrate every bit of data, hundreds of thousands of horizontal wells and the seismic data that's available, the earthquakes, information from sponsors and whatnot to map the faults. And so this is her fault hazard assessment on one graphic, and she's making her way now up into the northern Delaware Basin and into New Mexico to try to fill in this part of the map, which still has a lot of faults that need to be added. We know they're there. We just have to add the robust interpretation of them. And very excitingly, we have this 3D seismic data that the Railroad Commission has granted us the funds to access from Fairfield Geophysical. And Fairfield Geophysical has been very generous with how they're allowing us to use the data in a 3D survey here. And this is a profile you've now seen several times. It shows Lily's ongoing interpretation of these faults. And we're producing public reports every 3 months or so, and 2 of those reports on this interpretation are out and available, and another 6 of these reports will occur over the next year or so, as we take the interpretation and understand the depth of the earthquakes and Alexandros' work, what the pore pressurization is on these faults, and all the rest of that as we go. So what we've left then is these shallow earthquakes in the southern Delaware Basin, right here, where these earthquakes are demonstrably above the basement sediment interface, way up here in the levels used for hydraulic fracturing and up into the shallow injection above. And you can see these earthquakes in red on the lower right. So thus far in the Delaware Basin, we've talked about deep injection pressurization causing these earthquakes here and up in New Mexico. But this injection in Texas, these 22 wells right here have been ordered to suspend operations. And so that injection has gone down, and it'll probably go down close to 0 over time, while the rates of shallow injection in this area are going up. And you can see, though, how the earthquake rates are tracking the deep injection rates down. Black following purple down, while amber is going up. As amber is going up, though, to compensate for that loss of deep injection, other things are happening. And that's what's shown on the right-hand side. This represents Junga and J.P. Nico's analysis of pore pressure change from shallow injection. So injection in amber wells showing the distribution of the shallow injection. Hydraulic fracturing is also shown behind, and then earthquakes from that proprietary catalog in red. So what we're dealing with now is production of fluids from the shales, injection of fluids in the Delaware Mountain group, and the reaction of that system to that fluid withdrawal and that fluid injection. This is where satellite geodesy comes in and is a big help to us to understand. We use NSAR data, and I'm not going to talk about that method, but we collaborate with UT Aerospace and Ann Chen's group and her students to do this. And here is one example of this work, a paper that I published a year ago or so. What it shows is, in the center diagram, is 7 years of uplift in subsidence in the Delaware Basin. The cool colors represent subsidence of up to 17 centimeters. The warm colors represent absolute uplift. The subsidence comes from withdrawal of oil and water from the shales. In fact, the match of the footprint from left to center is just ideal. The uplift is more complicated. It comes from injecting into the Delaware Mountain group, pressurizing those formations and causing uplift. But keep in mind, if there's uplift like this in the middle of the subsidence bowl, that means that the inflation and the uplift is able to outpace the subsidence underneath it from fluid withdrawal. So there's been a lot of work on this, our work, other work, and this is sort of the compilation map that was available a couple of years ago, and it just shows all of the things that matter. The deep seismicity matters because there's a co-seismic signature on the ground surface from that deep fault offset. The shallow injection causes the uplift, the fluid withdrawals from production causes the subsidence, and the whole thing is just kind of an exquisite laboratory. We're looking now at this area we call Uplift Island 6. On the right-hand side are some snapshots, 2 years, 4 years, 6 years, and then 8 years through 2023. And there's a line of profile that goes across it right here. And you can see how it went from this curve to this curve and finally to the black curve at the end of the most recent data, showing you the change of the ground surface down on the flanks and up on the uplift as fluids have been withdrawn and fluids have been injected. So there's 3 million barrels injected every day. Much of it's trucked across the border from New Mexico into Texas, where our regulations are looser as far as shallow injection is. There are issues like legal action from injection trespass, loss of well control while drilling, the potential for mechanical or chemical compromise to the capping of CHO and evaporite strata, propagation of these faults along anisotropic directions, and then numerous surface flows that can result in these type of hyperbolic photographs. But this is something that, a picture was taken a few months ago in one of these areas where this pressurization has found a shallow well bore. The well is 60 years old or something, and that surface flow, that's what you want to call a geyser. And on the left-hand side is Katie's new work looking at all of these old vertical well bores, 250,000 old well bores that are in this system, and some of them being old enough that they may compromise the containment of the shallow injection from the surface. So I can stop here, and I probably will. I just took the cross-section that Lily and I built, and I superimposed it on top of Ben's diagram because I'm no artist. But it shows sort of the geomechanical complexity that we have to deal with. Here's the surface environment and the shallow injection and production from the Wolfcamp Shale sitting over the deep injection strata, and then the seismogenic basement below. So there's an effort that's underway, Lily and her colleagues and Peter on a new basement map, and that factors into this as well. So thank you. In the slides, I'm not going to go through these words. There are a whole bunch of conclusions, and so if you wanted to go back and say, well, what would he have said if he had time to read through all of these conclusions? This was what I would have said, but let's stop there. We still have time for questions, and thank you.
Thank you, Peter, for this excellent overview of induced seismicity in Texas, and we have some time for questions. Yes.
Start with a close one. I guess I'm easier to access. So, Peter, to the force here. You covered a lot of ground here. You made a very strong point for the deep earthquakes, what we call the direct pressure effect, that you pressurize the deep injection reservoirs, and that pressure goes into the faults that are in the basement, which is the opposite of what we concluded, because the argument that we made is, and you may have new data that support your statement, but our argument was that the faults in the injection reservoir would always experience a higher stress, poor pressure effect, direct pressure effect, therefore rupture before the deep basement ruptures. That's pure physics. So our conclusion was that it is necessarily this forelastic effect.
Yeah.
And you didn't talk much or anything about it. So I wonder if there's some new data that it was based obviously on the timing. When do the deep earthquakes occur relative to any shallow activity? Is there anything new that would actually make that case, or is it that you don't want to deal with elasticity? I don't know.
No. That is a sort of a one-dimensional conclusion that I did in fact make. So I believe that poroelastic stressing absolutely plays a role, because mechanically it just simply must play a role. The cases that we've worked, and now we're seeing this in Oklahoma, all of these cases have the faults that ruptured in basement interpreted to extend up into the strata used for injection. There's a direct hydrogeologic connection between those two things. So it's my personal belief, based on all the work that you channel and this other work, that poroelastic stressing matters, effective stress change matters, but what probably matters most is what is the hydrogeologic connectivity from the injection strata and down into the basement. Now, I know your question about the timing and about why we might get earthquakes so quickly and so early, I think is sort of part of your question.
Why do we get it in the basement instead of in the injection reservoir?
Yeah.
Because that would have a higher induced stress than the basement.
The answer I would propose as a hypothesis is the basement being so seismogenic, it is really the stress-carrying component of Earth's crust. And when we measure stresses that we use in these models, we're typically using a lot of data that comes from the sedimentary realm above. And so I'm concerned that we are inadequately characterizing the stress state in the basement and therefore the sensitivity of those faults in the basement to the stress change.
However, that argument actually works against you because it means the faults in the basement would be less likely to slip because the normal stress would be higher. So if the basement is the loading strong beam there, it would actually be the lesser stress faults that would rupture first.
So what I would say to this is where computational modeling plays such an important role in giving us an ability to look at the different contributions between effective stress change and solid frame stress change, that sort of thing. That's the primary role. But then you also have to think about, for the cases that have been very well documented, some of yours, the A&M work, other work that's been done in the Permian Basin, the stress change, the Coulomb stress change from the poroelastic contribution is typically about 10% as compared to the 90% contributed from the effective stress change, if you were to kind of take all of these studies on balance.
True. But we concluded this 10% change makes a difference.
And I think it does.
Farther. You know, it goes beyond the direct pressure.
Yep. So my conclusion is that we're in agreement. We just have come at it from a different angle.
I guess we agree that one numerical modeling is needed.
Mm-hmm.
However, I noticed that you guys are moving now more toward the reservoir that the pressure modeling is, right? And near surface pressure changes. So I guess there's a shift in the direction.
Well, we're not going to shift away. Scissor will go wherever the scissor leaders, Katie and JP and new people to be hired, take it. I am confident they won't leave fault rupture and seismicity behind because that's just too important for so many reasons. So that work will continue. It's just the emphasis now is understanding the proximal problem of what to do with 15 million barrels of wastewater a day.
Peter, thank you for this great presentation and excellent graphic. My question for you is about your opinion about the plans for the future, because you are not going to stop the oil production. You continue producing water, you need to inject the water. You are moving to shallow injection now. So you are creating a potential problem for the future, like, damaging the shallow aquifer. And that's already is in the table, no? That, how long can you sustain pressurizing those shallow aquifer until you get to a new problem, like a contamination of the shallow aquifer. So, because there may be a potential solution to bring the water to the south, no? And use pipeline, use other aquifers that has the potential to sustain this. And there is a possibility that you increase production in the basin, there is a new mandate. To increase production.
Something has to be done, Carlos. I mean, because you saw a glimpse of Katie's new work, Scissor's work on Friday, where she talked about estimating the future capacity of injection in the Delaware Mountain Group. And what she was showing is even if the entire rock volume of the DMG is managed perfectly, there's only 15 or so years left of running room to utilize that reservoir. But the production of water is going to continue far into the future. So something else has to be done. But keep in mind, this water is not only saline, it has other things in it that require that if it's going to be used for any kind of beneficial purpose, it has to be treated. And the volumes involved mean that is an economic challenge that is really far from being solved.
All right, we have time for one more question.
Great presentation. Thank you so much. So my question is about the last part of this seismicity rate that you talked about. It's dropping, but we need to consider it as a dynamic problem, and change of conductivity of the fault that was reactivated causes more dissipation of pressure, and maybe that has some effect on dropping the seismicity rate rather than just trucking the salt water.
Yeah, I agree completely, and we're very interested in that, Madi. And I'll just use your comment to show one more slide. And this slide deals with that question. What it shows is it shows this NSAR stuff I talked about. It shows these faults that Lily have mapped and the earthquakes. You know, these earthquakes are following these faults because these faults are transmitting pore fluid pressure and are being reactivated in an anisotropic mode. Also, what's happening across this whole system of injection at these injection wells is they're creating hydraulic fractures due to injection. And there's one realization of what the hydraulic fractures might look like, scaled by injection volume and oriented by SH max. So there is an anisotropic fabric that is very much activated by the pore fluid pressure, modulated by that pressure, and is a component of any modeling that really has to be done to understand how these pore fluid pressures in the reservoir evolve. And so there is this coupling of the mechanical effect and heterogeneity that really can only best be modeled computationally, I would say. That is, I think, a great avenue for research.
And since we got a question online, Norm, would you like to ask the question yourself, or you just read it?
Reading here. Okay. Norm Wells, there has been a lot of concern over monitoring earthquake activity, but not so much about monitoring injection wells and getting an understanding from the source. How are we supposed to understand the pore pressure changes in injection rate, temperature, volume, that would be the primary contributor to the stress changes of the fault? Well, you know, that is a question that addresses the data deficiency that we have, the data deficiency in reporting. We are hampered in our modeling by having very many downhole and high quality indications of pore fluid pressure change in the reservoirs. The Railroad Commission is addressing this now because they're thinking about changing how they conduct permitting to require more downhole pressure surveillance. And so the regulator realizes that. I know that many of our scissor sponsors, the industry, recognize that downhole pressure data does, to your question, go directly to the source. What is changing at the injection well? So we don't have as much data as we need now, but there's a movement from the regulator and from industry to start to provide that. But it's going to take collaboration. It's going to take the public and researchers to work with that data to inform the models and the prognoses to understand how to manage the water.
Great, thank you. We ran out of time, so let's thank again Peter for this wonderful talk. Thanks for coming.
All right, thank you.